Gaussian mixture model estimation. Let's try a hack. So right now we sort of don't have any proof or um, any formal intuition of why would this hack works. Why would this hack work? I won't give it to you in this section, but let's try something that we saw in k-means. Why don't we sort of follow a similar approach? And to do it by hand, to go step by step, is very important. So this is like all of the steps. I will show you the conclusions or results, but all of the steps you will fill in as your homework, so you can appreciate and see with your own eyes and hands and brains what is happening. So a mixture of two Gaussians. Nothing by that. So we have a probability distribution, likelihood of parameters for two Gaussians. Those are the weights of those Gaussians, probabilities of class K and class K plus 1. And expanding the Gaussians. So that's what we're dealing with, and let's make a few assumptions for this. Let's assume that those Gaussians are equally likely, so the class probabilities are 1/2, and let's just fold all of our parameters, mu1, mu2, and sigma. Now we are in the two-class case, not in the arbitrary k-class case. So just two Gaussians, one-dimensional situation. All of the parameters are folded into one single vector theta. So if we assume that mu's are known and sigma is also known, and well, just a note that sigma is the same here for both Gaussians, just the mu's are different, but everything is known. If that is true, then as you will show in your homework, probability of class 1 given a data point and probability of class 2 given a data point is can be expressed by this expression. And class 1 is e to the negative linear function of x, and class 2 e to the positive linear function of x. Well, does it remind you of anything? I hope so, because if we denote this by, say, z and multiply this expression by 1, z over z, then what you will get is, well, let's denote this part by z. That will be more interesting. E to the minus z, e to the minus z. Okay. And this one is e to plus z. So what we will get is e minus c over 1 plus e c. So if you look at the first one, 1 over 1 plus e minus c, and at the second one, you immediately see that this is logistic regression, linear boundary, and probability of the class will behave like that around the boundary, right? At the boundary, it will be 0.5, and then go towards one class and towards another class. Or this is actually probability of class 1 This will be the distance. That's your decision boundary. This is the distance where your point is located, and that's how it will look like. Uh, okay, and you will play with this, derive what W1 and what is W0. You will derive this expression to make sure that I'm not lying to you, that you can trust me too much, you know. And then you will also then explain, oh, if this is probability distribution, why it's sigmoid, why doesn't it integrate to one? At least you will understand that too. Don't ask me that question, that's your homework. And yes, another thing is softmax. But imagine now that we have mixture of multiple components in this case, right? So that's where those ideas come together with the Gaussian mixture model, but that's not everything. So what we've gotten here is class posteriors, right? Given the data, what is the class, what is the probability of this data belonging to class one? That's the posterior distribution. Let's make another assumption. Assume that we know sigma, but we don't know mu's. So before we knew everything and we figured out what the class posteriors would be, the posterior probability distributions of the classes. Now assume the mu's are not known. How would we go about it? Well, let's look at the mixture of our two Gaussians again. And what we see is, well, nothing new, what we saw before. Um, our likelihood for all of the endpoints, this is for one point, so this is exactly this uh, likelihood of one point, and then we are still holding on to our ID assumption. And by this assumption, we can say that probability of this data set, of observing this data set, is just the product of the local likelihood, or likelihoods of the parameters at each of the points. And as you will show in the homework, the derivative with respect to the mean of this likelihood, uh, actually of the log likelihood of this part, if we take a log of this, that's what the calligraphic L stands for, log likelihood. And once we have the log likelihood, you will show that the derivative of the log likelihood is nothing but the posterior class posteriors that we saw on the previous slide. Probability of k given x sub n. Let me show you this, depending on k, times x minus mu normalized by the variance. So, we're getting somewhere already, but not quite yet. So, just a reminder, we know the sigmas, but we don't know mu's, and we now need to estimate the mu's. We know how to estimate the class posteriors. For every data point, we can compute the class given the mu's and the sigmas, right? That's what that meant. That slide meant. Now, you will show what's the derivative of the log likelihood with respect to the mean. And next, you will show what's the second derivative of the log likelihood with respect to the mean. And as you see, well, that's easy if we ignore the derivative of posteriors, class posteriors, then derivative of this is nothing but 1 over sigma squared. Well, the minus sign follows off over there. So simple algebra. I already solved it for you. Okay, now I have to think of a harder homework. I'm just kidding. And let's continue. What will happen next? Well, what will happen is you will use the good old Newton-Raphson update that we've used to solve logistic regression already in this class, which is an updated mu equals the old mu minus the ratio of the first and second derivatives. And once you do that, you will show that the new estimate of the mu, or the optimal for this sort, or the, well, not the optimal, but the new updated value of the mu is nothing but sum of the posteriors times the point value, so sum across integral or sum across the complete data set divided by the um, sum of all of the posterior values. Does it remind you of anything? I hope it does, because remember, in the last lecture, the k-means, soft k-means, and hard k-means update was exactly this. It was the sum of across all the points with responsibilities times the values normalized by the sum of responsibilities. Oh, look, responsibilities are class posteriors. So when we estimate Gaussian mixture models and when we do mixture modeling, our maximum likelihood estimator or bar estimator uh, in this hacky way is just class posteriors. So what is hacky about it? Well, let's see. So GMMs and k-means, right? Responsibilities and posteriors over latents. The responsibilities in k-means are posteriors, are class posteriors, and the update is maximization of the likelihood because we maximize the likelihood when we set the mu to this value. So both are hacky approaches to solve latent variable problem using the same general technique. And this technique is called expectation maximization, which is a meta algorithm. And the point in both of the concrete methods, GMMs and k-means, and many others, is that at first we set our parameters to some arbitrary values. Then, next step, we estimate class posteriors given our data and those arbitrary value parameters. Then we compute the maximum likelihood estimate of those parameters given the class posteriors that we just estimated. So maximum likelihood estimate usually is computed with respect to the current parameters, but we are using previous parameters that we obtained by using the previous values of guessed parameters in the estimate of the new parameters. So it's kind of like if we were doing maximum likelihood correctly, not to say that expectation maximization is incorrect, but if we were doing just the maximum likelihood estimation, then the parameters would have been the same, like they would have been in the same kind of iteration. We would know the values of sigmas and mu's and would just maximize them. But here, because we do need to use the posterior distribution in the MLE formulation, in the maximum likelihood estimation of the parameters at the next step, we have to go, because right now it's just a hacky approach, we have to go with our previous estimated parameter values, or guessed in this case. 0 will be guessed and estimated and keep repeating until convergence. Will it converge? Well, the next section or episode will be exactly about that question. Well, in fact, it will be about expectation maximization.